Hey, what's good, you guys? Listen, we are going to look at another type of optimization, and I believe in the past we looked at the cost. We looked at optimization of volume and surface area, right? Now we're gonna be looking at optimization in the context of motion, right? So this is the calculus of motion, okay? And those of you that are doing physics in technical science and physical sciences, I believe that you guys have done vertical projectile motion. So optimization can actually be, applied to that kind of context. So that's what we're going to be looking at right now. So please just take a look at the question. We are looking at question 3. Yes, not so difficult as long as you understand the concept. I mean, if they were to bring this one in any exam, right, it would be a giveaway, because in my opinion it's the easiest to understand. There isn't any prerequisites that are needed, like the ones that we've covered. Because if you look at number 1 and number 2, right, this involves surface area and volume. So if you've got no idea what is surface area, what is volume, automatically you lost, you get what I mean? So that is to say that to fully understand, what we've just covered in the past 2 videos, you have to ensure that you conceptually understand the meaning of surface area, the meaning of volume. Do you get what I mean? It mustn't just be a thing whereby you're just looking to collect marks. It needs to be something that you understand conceptually. Okay, like, can you link your understanding of these concepts to real life? You get what I mean? Yes. So now let's quickly jump into this. Okay, I'm just going to read the question quickly with understanding, of course. So a tourist travels in a car over a mountainous pass during his trip, right? The height above sea level of the car after 2 minutes is given as, so there's a function for the height, and the function is in terms of t, so that means, and the t is time, right? So that means we're gonna be deriving with respect to t, which is time. Okay, now they're saying after 2 minutes, they're saying the journey lasts 8 minutes, so in total we've got 8 minutes. Okay, now how high is the car above sea level when it starts its journey on the mountainous pass? Okay, and here you need to understand that at the beginning of the journey the time is 0. Okay, before you travel any distance, the time is 0. So if you substitute your 0 there by the t, you would definitely be able to know what is the distance before the journey starts. Okay, so, and I'm pretty sure you guys can see that this is just going to be 100 meters, because you put a 0 there, everything zeroes out. 0 there, 0 squared is just 0, becomes not, so we're not going to waste our time with 3.1. We know that initial distance is going to be 0, of course. Okay, so now let's go to 3.2. Calculate the car's rate of change, okay, of height. All right, rate of change of height. Remember, the subject formula is the height. Immediately when you say the rate of change of height, that means the first derivative. Okay, that is the first derivative, the rate of change of height. So because the first derivative has got that kind of definition as well, the rate of change. Okay, so if you understood the derivative conceptually, you would know that the rate of change is basically the first derivative, and then the second derivative is acceleration. Okay, so yeah, take note of that. So calculate the car's rate of change of height above sea level. So what we're going to do here, we're going to say, okay, we know that our formula is given by this. Sorry about that. Our formula is given by this. So s of t, which is just distance after a certain period of time. Okay, s of t is equal to 5t to the 3 minus 65t squared plus 200t plus 100. Okay, so now that's just the distance after a certain period of time. It depends. So it depends on the time, right? So now the time is unknown, so we have to first find the derivative, then we plug in the given time. Okay, so this is a function of time. All right, so if you were to plug in any value, right, if you were to plug in any value right now, you'd get the height. But if you are plugging in a value into the first derivative, you are no longer getting the height, but you are getting the rate of change. In other words, now the answer that you're getting tells you how fast the height is changing at that particular time. Do you get what I mean? And then the second derivative, if you plug in any time value, if you've got the second derivative function, then you are going to be getting how fast the car is accelerating, you know. So okay, let's do this. So now we're just gonna say s prime, which is the same as ds, ds over dt. In other words, the derivative of this function with respect to time. So this is just going to be 15t squared, okay, minus 130t, and then this is plus 200. You guys know that the derivative of a constant is just going to be 0. So this is our rate of change. You know, this is the function for our rate of change. So if you're asking about the rate of change, this is a function that I'm going to be using, and depending on the time, obviously, because you can see that this is a function of time. It depends on the time at which you're talking about. So now they're saying calculate the car's rate of change of height above sea level with respect to time 4 minutes after starting the journey. So our time is 4. I hope you guys agree. So we're just going to substitute our time. So 15 and then 4 squared minus 134 plus 200. Okay, so now that's gonna tell us how fast the height is changing after 4 minutes. Okay, plus 200. Okay, let me just check if everything has been substituted correctly. 15, 4 squared minus 134 plus 200. Okay, we're good to go. Right, minus 80 meters per minute. So it's meters per minute. Yeah, it's meters per minute. So now that tells us that because our answer is negative, that means that now the height is decreasing. Okay, if the answer was positive, then that would mean that the height is going up. Does that make sense? So now let's go for another one. Another one. Remember, rate can be negative as well, so you must bear that in mind. It depends on whether whatever rate that we're calculating, is it an expansion or do you have a contraction? Right, so 3.3, let's just read that quickly. So interpret your answer to question 3.2. We just spoke about it, that because the rate of change of height is negative, that means our height is decreasing. In other words, the car is traveling in a mountainous area, but it's actually coming down. Okay, it's not going up and up and up and up. That's why the height is not, the rate is not increasing. If the rate was increasing, then that would mean that eventually our car would end up at the highest level as possible, in terms of height. Okay, so 3.4. Okay, they're asking how many minutes after the journey has started will the rate of change of height with respect to time be a minimum, right? So they're talking about the rate. Okay, the rate of change. You guys already know the rate of change is the first derivative. If they were talking about the acceleration, then we would go ahead and calculate the second derivative. But if they're talking about the rate of change, definitely it's the first derivative. So we're just going to take our first derivative and set it equal to 0. That's when we're going to find the time at which that function is at minimum. Okay, so yes, how many minutes after the journey started will the rate of change of height with respect to time be a minimum? Okay, so we'll set that equal to 0, and I'm sure you guys have done what we call, so this is 3.4. I'm sure you guys have done the plotting of the cubic function, because what we are looking at here is basically a cubic function. And a cubic function, according to me, from what I've seen, it's basically a combination of two quadratic functions. One is concave up, the other one is concave down, or alternatively you could say one is a smile, the other one's a face. I mean, not a face, but a frown, sorry. And then and when you calculate the first derivative and set it equal to 0, basically you find values of x where on one side the function is either minimum or maximum, and on the other it's also either at minimum or maximum, right? So yeah, so if you are trying to find the minimum value, definitely, and with a quadratic function, obviously that means that we are going to find two values, right? And we need to pick the one that gives us a minimum, not the one that gives us a maximum. Okay, right? Because you must, like I've already said, if you remember when we were calculating the stationary points by the cubic function, there's always two values. There's one value for the maximum, there's another value for the minimum, but we are looking for the minimum one. Okay, so usually you'd have to substitute and figure out, okay, which one is giving me a minimum and which one is giving me a maximum value. Then you would know, okay, at this point my function is going to be at maximum, at this point my function is going to be at minimum. Okay, so we've taken the first derivative, which is basically the function for our rate of change, and we set it equal to 0. So we're going to solve this function, and obviously we do not need, we can easily use our what we call our quadratic formula, right, to find the values of t, which is what we're looking for, because remember they're asking for the time at which this whole function is at minimum. Okay, Now, so we know t is going to be minus b plus minus the square root of b squared minus 4ac divided by 2a. Yeah. Well, you see, using what we call the factorization method, that's not a problem as well. It's just that personally, when I realize that, you know, I'm spending a lot of time thinking about the factors, then I just decided, no, I'm gonna use, you know, the quadratic formula, because you really don't want your time to get wasted. So 24,36, or the other one is what? The other one is 1,64. So both of these actually qualify to be they actually qualify to be our solution, because they're both positive. You see, if one was negative, then we'd say no, that's invalid, because it's not possible for time to be negative. Do you get what I mean? But unfortunately, in this case, both of them are actually positive. So that means that we don't have a choice but to go back to our cubic function and plug in these values and see which one gives us a minimum value. Okay, so as of t, you guys already know it's 5t to the 3 minus 65t squared 200t plus 100. So now we're going to find s of 24,36 and s of 1.64, just to figure out what is the value there. So in place of the t, I'm going to put 24,36 and see what value I'm getting. 5. So let me just say 24,6 equal to, so that I have it as my answer. So I'm just going to say 5 times answer cubed. Alright, 5 times answer cubed minus 65 answer squared 200 answer, so that I don't have to keep on typing the 24,36, you know, might waste my time. Okay, so we've got 401 40,119.28. This is definitely giving us a maximum. I'm telling you. So let's now substitute the other value, which is 1,64, and see what's the corresponding y value that we're getting, right? If they were asking for the maximum, then this would definitely, this t value would be the one that we are going with, if they were asking for the maximum. But now they're asking for the minimum, so that means we're looking for the t value that's giving us the lowest possible corresponding height value, because remember, this is the height in meters. Okay, now 1.64, let's do the substitution for that. So it's just going to be 5 answer cubed, okay, minus 65 answer squared 200 answer plus 100. Remember, my answer is just 1,64, and as predicted, this is 275,23. Now this is the t value. This is the t value. So the t is 1,64, because it gives us the lowest. It gives us the lowest, you know, height, right? Okay, it gives us the lowest height. So that's it, you guys. So how many minutes after the journey has started will the rate, right? Will the rate of change of height with respect to time be a minimum? Okay, so after 1,64 minutes, right? After 1,64 minutes, so that's like probably 90 seconds, because this is 60 seconds. This is around about 30 seconds. Let's just say 40 seconds. So this is probably 100 seconds. So after 100 seconds, but the thing is now they want it in minutes. So that's why we have to express our answer in minutes. But if we were allowed to express it in seconds, would say after 100 seconds, approximately 100 seconds, the rate of change of height will be at minimum. Okay, and that's it for this video. I hope you guys enjoyed it, and all the best. Peace out. Right, guys, let's now quickly look at the last question, right? And probably one of the trickiest of them all, when calculus of motion is concerned. So here's the question: how many minutes after the journey has started will the rate of change of height with respect to time be a minimum? Okay, so look, by 3.2 we calculated the first derivative. Okay, and now everything after having calculated the first derivative 9 out of 10 times, it's going to be based on the very same first derivative function. Okay, so now let's check what is the function for the first derivative. So 3.4, the function for the first derivative is 15. So let's just write it out nicely. S prime of t is equal to 15 t squared minus 130 t, and then plus 200. Okay, so this is the function that we're going to be focusing on, because on the previous question this is what we used. Okay, so now we're talking about minimizing this function. Okay, so how many minutes after the journey has started will the rate of change of the height with respect to time be at minimum? So this is the rate of change of height. Now they're asking when will this be at minimum? Okay, so another misconception is to take this function and set it equal to 0. So when you set this equal to 0, you're just going to find the values of t where the rate of change is basically 0. Okay, yeah, and that is either at the beginning of the journey or towards the end of the journey, when the car is not moving. Do you understand? So now to optimize this, you can either use x is equal to, remember the formula that we were using in grade 11, x is equal to minus b over 2a. When we were finding axis of symmetry, it's the very same formula. But in grade 12 we use calculus, right? So in other words, this is not necessary, although it works, right? It takes a little bit of time, to be honest with you. This is what we were using in grade 11, but now we're going to be using calculus. So we're just going to derive our rate of change one more time, and then we're going to find this function here. So that's 30t minus 130 is equal to, we set it equal to 0, then we solve for t. So 30 is equal to 130, and then t is equal to 130 over 30, which is just 13 over 3, and that is 4.3 3. Okay, so that is minutes. Okay, so meaning that this is how long it's going to take after the journey has started, for our function to be at minimum. In other words, for the rate of change to be at minimum. Okay, for us to achieve the lowest possible rate of change. So it's never gonna go any lower than this. So this is not the rate of change value, but we're just saying that at time 4.33, if initially the rate of change was decreasing, then it will start to increase. Or if it was increasing, then, but obviously if we're finding the minimum one, that means initially it was decreasing. And then after this time here, then it's going to start increasing. So that's why we call it the minimum value. So the situation is like this. And then at this point, that's where you have your 4.33. And then, so meaning that this side, that's when the rate of change was, the rate of change was decreasing. And then after this time, the rate of change is going to start increasing. Remember, this is the function for the rate of change. So that's it. Thank you very much. And I hope you guys enjoyed the lesson. Until next time.